Let's go ahead and introduce this next section with hypothesis tests. We're going to do the same basic concept that we did with StatKey earlier, and that is we're going to generate ourselves a sampling distribution, the normal curve, and the only difference between StatKey and what we're doing here is that we assume it is a normal curve as opposed to, oh wow, it happens to look like a normal curve most of the time. So we always assume it's a normal curve, and that's why we have to check some things. Once we've generated that curve, we actually shift that curve so that the null hypothesis, either mu or p, is in the middle. So even though the curve is based on the sampling distribution like you would generate for a confidence interval, we just pick up that curve and shift it. So let's say your x bar, your p hat is really down here, and your confidence interval says the sampling distribution looks like so. We pick that up and just slide it over. StatKey actually does that internally. It just slides over that distribution. When we generate our graph, are going to use the standard deviation from the sampling distribution, but we're going to put mu and p in the center. So that's kind of our little workaround of how we do that. Once we've generated that curve, we have mu or p at the center, then we look at our x bar or p hat. We look at how far away they are, and we then shade in the area outside of that area. Now if it's a two-sided test, we might end up shading in both sides. Otherwise we might just do above or just below. Now to actually figure that out when we're dealing with the normal curve of how far away this is from here, we need to convert everything to a z-score. Now a z-score is going to follow the same basic pattern that we're used to. Z is equal to the value we're interested in. So I'm going to write the old z-score formula that we're used to. The value that we're interested in minus the center divided by the spread of the distribution, the standard deviation. That's the old formula that we use for calculating just typical normal z-scores. Now if we're going to use this for sampling distributions, we have to get a little bit more advanced. We are going to say our z-score is equal to our statistic over here minus our parameter, or our null. So we have a statistic minus a parameter, and that's all going to be divided by the standard error. We're going to take that and divide it by the standard error, the standard deviation of the sampling distribution. Now for means, we're used to seeing that as the central limit theorem. So if we're talking about means, it would be our standard deviation over the square root of n, or sample standard deviation divided by the square root of n. That would be plugged in down there in the denominator. When we're talking about proportions, it's that really unbeautiful formula of p times 1 minus p over n, all square root, and that would plug in down there. It tells us how wide our sampling distribution is. In essence, it's really just that same basic z-score formula we're used to, but we need to generalize a little bit to make sure that we can use it for both means and for proportions while working on hypothesis tests. Finally, the last step, once you have a z-score, is to use that z-score with some sort of either table or our calculator function, normal CDF, in our TIs, to go from negative infinity, since it's on the left side, up to that z-score, or negative 99 to, let's say our z-score was negative 2.1. We would calculate that, and that would be our p-value. So whatever that equals is the p-value, and that's what we're trying to find as we do these normal curve calculations.